We've seen that we can use definite integrals to solve the geometric problem of finding areas in a plane. So let's look for some other geometric problems that we could solve using integrals. If we can find areas in a plane, maybe we could find volume in space. So let's, just to have a problem to start with, let's look at this one. So suppose we take a square-based pyramid and we cut off the top so that the top is a 4-inch square. The bottom is a 10-inch square, so it's gonna flare outwards like this, and the whole thing is 12 inches tall. So it's going to be 12 inches here. Something like this. You know, using our experience from how we use definite integrals to find area by slicing up some region into a convenient shape, maybe we could do the same thing here. If you imagine slicing this up sort of vertically like this, the shapes you get aren't very nice. They sort of change a lot. They change in character. Sometimes they're rectangles, sometimes they're trapezoids. It's kind of a mess. But if we imagine slicing this thing horizontally like this, so there's one slice, right? Here's another slice. All of these cross sections are squares. Right? The one at the top is 4 inches across, the one at the bottom is 10 inches across, and the length of the side of these squares varies from 10 to 4 as we move up the pyramid. So it seems like this would be a nice way to slice the pyramid. Also, if we take one of these slices, right, so it's a square like this, whose side length is somewhere between 10 inches and 4 inches, what is the volume of this thing? Well, you know, if this is the bottom cross section, then it's 10 inches this way, it's 10 inches that way, 10 inches wide and 10 inches deep. But how tall is it? Well, it's sort of infinitely short since it's a cross section, and so since the height is an infinitely small quantity, we should call it d of something. Maybe dz, since it's going in the z direction. So the area is the area of one of these cross sections. I'm sorry, the volume of one of these cross sections. It depends on how high we are, so that's going to be a function of z, and it's the area at that height times a tiny little height, dz. So you see we've broken up the problem of finding the volume of this entire thing into finding the volume of just one tiny piece of it, and then the total volume will just be the integral of, right, the area at z times dz. So we're just adding up the volume of all the little slices, and I guess we'd better go from height 0 to height 12. Right, so all we have to do to use this idea is come up with some way of writing what is the area at height z. So if you think of the side length as a graph, right? So at the bottom we're at 10 down here, and when we get up to the top at height 12, we're at width 4, like this. And in between, it just varies linearly because it's a pyramid, right? Pyramids have flat sides. So we just need to express this relationship. So when the height is 0, this is a linear relationship, right? Here I have the height, and here I have the width. It's maybe a little easier to see what the right equation should be if we flip these so that the height is horizontal and the width is vertical like that. That means that at z value 0, the width of this square is 10. At z value 12, the width of this square is 4. And in between, we have a line. Okay, so the intercept of this line is 10, and this it's going down, so we need a minus. The slope, let's see, it's decreasing 6 over a run of 12, so that's a slope of a half z. Okay, so this tells us the side length at height z. Right? Just to check, you can plug in when z is 0, this gives us 10, and when z is 12, this formula gives us 4, which is what it was supposed to be. So this is the correct formula. So we need to remember we're trying to write down the formula for the area at height z. Well, for a square, the area is just the square of a side length. So the area at height z is the square of this side length function. So z 10 minus 1/2 z squared. Right. So now we can use this together with this idea up here for calculating the total volume. So let's give it a try. So integral from 0 to 12 of our area, which is 10 minus 1/2 z 10 minus 1/2 z all squared dz. All right, now that we have this definite integral written down, we can temporarily forget where it came from and just evaluate the integral. Expressing the integral you want is usually often the hard part, and then calculating the integral is somewhat routine, hopefully at least. So it seems like maybe we should start out by multiplying everything out. So integral from 0 to 12, let's see, multiplying this out, we get 100 minus 10, right? Twice the product, so 10z plus 1/4 z squared dz. All right, now we can integrate. So 100z minus 5z squared plus 1/12 z cubed. And now we need to evaluate at 0 and 12. So when we plug in 12, we're going to get, let's see, 1200, I guess, minus 5 times z squared. So 5 times 12 squared is 144. I'll have to work that one out. Plus 1/12 times 12 cubed. And then we can simplify this. This 12 cancels that, and we're left with 12 squared, which again is 144. Okay. So 1200 minus, let's see, 5 times 144 plus 1 times 144 is 4 times 144. Okay, calculator time. So 1200 minus 4 times 144. That's 624. And this is in cubic inches, since all of our lengths were measured in inches before. Actually, I didn't plug in the 0, but when you plug 0 into this, right, we just get minus 0, so that doesn't actually change anything. All right, so this idea that we had of taking some solid shape and slicing it and finding its volume just by integrating the area of each slice, that actually worked. It's sort of the three-dimensional analog of finding the area in a plane. To find the area in a plane, you integrate the function that tells you how high the slices are. To find the volume in space, you integrate the function that tells you how much area each slice has. And that works in general. So if you have a solid shape that extends between two x values, say from x equals a to x equals b, and you know the area of a cross-section as a function of x, then the volume is just the definite integral from a to b of your area function. Let's see how this works out in another example. So here we have a tent shape whose cross sections in the x direction are made up of isosceles triangles, whose height is half of the hypotenuse, and all of these units are in meters. Let's find the volume of this. Notice that the bottom edge of this tent, along this front edge, it follows the graph of y equals x squared minus 1. And just to get sort of a feel for what this shape actually is, first of all, the isosceles triangle cross sections, here's one, right, and the base is, we can't see, here's another. They don't quite look like isosceles triangles, but that's because we're viewing this whole thing from an angle. Right, here's the biggest one right here. And all of these are isosceles right triangles whose hypotenuse is twice the height. So the height is that way and the hypotenuse is like this. Here's a 3D picture of this thing, so we can rotate it around. You see it's has these sort of two curving sides that meet at this peak at the top. If we turn it to look at it from one end, you can see there's the cross sections, right? The largest cross section is sort of on the skyline here, and all of the other cross sections are these isosceles right triangles that are nested inside. Okay, so with these cross sections in mind, let's write down an integral that would give us the volume of this thing. Well, we know that the volume is, if we can find an area function for the cross section, the volume is just going to be the integral between a couple bounds of the area, the cross-sectional area. But these cross sections are all triangles, so this is going to be the integral from A to B of the area of a triangle is 1/2 the base times the height. Okay, and actually something that isn't stated in this problem is this front corner is at x equals 1, and the back corner, which is hidden back here, is at x equals minus 1. So our bounds are going to be from -1 to 1. Okay, 1/2. The base times the height. Well, the height is just 1/2 of the base. So let's look at the base, right? The x-axis is running this way, and this front edge is given by y equals x squared minus 1. So that the base is twice that, right? Because for every cross section, you have a value here, that's x squared plus minus 1, and then here's the same value. So the base is 2 times, so the base is 2 times that function. Well, really, we want this length to be positive, so we should take the absolute value of this, and between -1 and 1, this is negative, so we need to turn this subtraction around to make it positive. So 1 minus x squared. So that's the base. And then the height is half of the base, which is just 1 minus x squared dx. All right. So let's see. Inside our integral from -1 to 1, these cancel, and we have 1 minus x squared squared. All right, so finally we have the integral that we want written down. We just need to evaluate this integral. So maybe the right place to start is multiplying everything inside out. So -1 to 1. This is going to give us 1 minus 2x squared plus x to the 4th dx. Now we can integrate, so we get x minus 2/3 x cubed plus 1/5 x to the 5th. And we're going from -1 to 1. Actually, this would be a good time to use our shortcut for integrals of even functions on symmetric intervals. Our shortcut said when your function is even and the interval is symmetric about 0, then the entire integral is twice the integral from 0 to one end. So that's going to be a little easier to evaluate. So let's do it that way. Of course, that doesn't change what the antiderivative is. The antiderivative is still x minus 2/3 x cubed plus 1/5 x to the 5th. But it makes our bounds a little easier because now we get to plug in 0 for one of our bounds. And since this is a polynomial with no constant term, when we plug in 0, we're going to get 0. Okay, so 2 times, now we can plug in 1 minus 2/3 plus 1/5. And then when we plug in 0, we get 0. So, officially speaking, there's a minus 0 right here, but that doesn't change anything. So 2 times, let's see, to add these together, we, I guess, need the common denominator 15. So 15 over 15 minus 10 over 15 plus 3 over 15. So 2 times 15 minus 10 is 5/15 plus 3/15 is 8/15. And then times 2 is 16/15. And since all of the distances in this situation were measured in meters, this is a cube in cubic meters. All right, so you can see that if we have some way of measuring the area of a cross section, or if there is some way of slicing this thing up so that the cross section has an area that we can write down, then this formula lets us calculate volumes pretty quickly.